Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host, as usual, is Tobias Macey, and today I'm interviewing Zsolt, Dollenstein, and Jimmy Lai about LibCST, a concrete syntax tree parser and serializer library for Python. So, Zsolt, can you start by introducing yourself?
So my name is Zsolt. I've been working for Meta/Facebook for the past 6 years. I've been maintaining libcst actually since just when the pandemic started to hit Europe. So this is like a pandemic project for me. It's like 2020-ish. I have an 8-year-old son. I'm big into video games. Yeah, that's me.
And Jimmy, how about you?
I'm Jimmy. So I was an engineer in Instagram while working on libcst since the beginning, and right now I'm an engineer at Kata. So yeah, I'm a big Python fan. I have been using Python for 10 years, and I do share what I learned about Python in local meetup and Python conferences.
And going back to you, Zsolt, do you remember how you first got introduced to Python?
I had to go deep onto this question. So I remember at my previous company, they threw me in the deep end. They had some massive Django Python 2 code base. They told me to do some minor infrastructure features. And that's when I realized that C++ is not the best language in the world, but instead it's Python.
And Jimmy, do you remember how you got introduced to Python?
I think it's back to when I was at school, when I tried to learn data mining, data analysis. Python was used in the course. So I like it that a lot of libraries are provided. It makes data mining or machine learning very easy.
All right. And that brings us now to the libcst project. So can you describe a bit about what it is and some of the story behind how it came to be and sort of what was missing in the ecosystem for syntax tree parsers that made this a necessary project?
In Facebook Meta, we have a lot of large code base that is multi-millions lines of code. So at Instagram, we have monoliths that is a few million lines of code. So we have a lot of different problem that is at large scale to solve. In terms of linting or co-modding, we have a lot of challenge. So in the beginning, we try to look for some open source tool to help us build customized linters and also co-mods. And we didn't find a good one, so we decided to build this libcst. In terms of co-mod, so Facebook has a co-mod open source library that allow you to modify the code or match some code pattern using regex. But regex is not able to robustly modify the code or match the more complex code pattern, so we couldn't use regex. And later, we also try to look into the available open source syntax tree parser, but the built-in syntax tree parser in Python, it doesn't provide concrete formatting information like space, and those are needed for co-mods because you will want to convert the source code as a syntax tree, modify the syntax tree, and convert it back to updated source code. And there are some available parser or co-mod tool, but they are not very convenient for us to use. So we end up decided to build the implementation of concrete syntax tree, libcst.
I have my own take on this. I wasn't there when the project originally started, but I started, maintaining this as a kind of like a power user. So the reason I flocked to libcst personally is because I tried lib223, which is another concrete syntax tree implementation that actually Black, the popular formatter, uses. And it's just I mean, it gets the job done, but it's so low level, right? So like you have to keep in mind how the CPython grammar is implemented and then like fiddle with low level CST nodes there, which is great for a formatter like Black, which basically only manipulates white space. Not so great for, 99% of the other use cases where you want to write code mods. The major things in libcst, I feel like, are like a relatively high level API where you can reason about your code as you would, normally as a normal human being. So you have this high level API that's also type safe. I mean, it's not impossible, but it's hard to shoot yourself in the foot compared to an untyped CST library like lib223 or other ones as well. I don't want to like pick specifically on lib223 because it's a great library. So those are the two main selling points for libcst for me.
A lot of people might be familiar with the idea of the abstract syntax tree, and I know that the concrete syntax tree is a bit above and beyond that because it preserves some of the extra information like comments and white space that aren't preserved in the abstract syntax tree. And I'm wondering if you can describe some of the situations where that maintenance of the extra information is necessary or useful as compared to use cases where an abstract syntax tree would be the preferable approach.
Yeah, I mean, so I get this question a lot from people who are not familiar with this space. The most concise way I can describe this is AST is useful for machines and for people who want to reason about like the semantics of the code, like what the code is intended to do. The CST is useful for like presenting the code to humans. And so, yeah, as you mentioned, like the CST includes a bunch of additional stuff compared to AST, like, I don't know, white space, comments, extra non-semantic commas and parentheses and these kinds of things. That's the main difference. And in terms of like the situations where the CS, like preserving like these syntactic trivia would be important are, I guess, where you have to interact with humans because you want to present the code in a particular way to these humans. Like, I don't know, maybe you want to keep existing formatting choices, or you want to order some things in a certain way and stuff like that.
I think from the use case of linting and command, we do need to preserve those formatting information. For linting, very common feature of linter is to ignore some linter errors adding comments. So in order to skip some specific errors, we would need to be able to parse and analyze the comments to figure out if it's ignored comments. Then in your linter framework, you can ignore some errors, not showing them to user. And for commas, it preserve the formatting information is very important because if you don't do that, when you just modify a small piece of the code, you may end up reformatting the entire file, and the generated diff will make it hard to understand by the user because they cannot see what exactly is changed from the command logic. So it's important to preserve the formatting information.
Yeah, exactly. And just to underline this, most of a lot of our code mods that are shipped with libcst are about manipulating type hints and lint suppressions and comments and these types of things.
In terms of the overall ecosystem in Python for concrete syntax tree parsers, there are a few of them around, and I'm wondering what it is that libcst has over and above them that made it a useful exercise to build that versus just taking one of the existing projects and extending it, or either upstreaming the changes or forking it, maintaining your own version, and sort of what are some of the core sort of architectural requirements that you wanted or needed that made it worth the effort of starting a completely new project?
I am not aware of any CST implementation that's type safe apart from libcst. So I'm a fan of type hints in general. So I might be extremely biased here, but like that's a killer feature, like in and of itself. The other thing that libcst provides that others don't are, as I mentioned, like a high level API where you can manipulate code CST nodes that are kind of logical. Validation, it's very hard to accidentally produce invalid code that has syntax errors, for example. Generally easy, like as part of writing code mods in libcst, you generally will eventually write code that, emits some Python code. And like one of the very big disadvantages of a CST library compared to an AST library is because it includes all of these syntactic trivia, when you're constructing CST nodes, there are tons and tons of parameters that you have to like just remember. And libCST provides an API, I think, that is pretty convenient to use because there are some sane defaults where, I don't know, like if you have a list, you can forget about making sure that the commas are in the right places and whatnot, because libCST will figure that out for you and things like that. So like some of these features are implemented in some CST libraries, but none of them like combine all of them.
I want to add something. So libCST, it starts as concrete syntax tree parser, but after we continue to develop on, it's not just a concrete syntax tree parser anymore. It also provides convenient API for traversing and modify the tree. We have transformer API and major API, which can allow you to describe a pattern or a shape of a subtree you want to match. It also provides some static analysis that adds metadata. So that way you can build some higher level linter and comma easier. We provide position data that is useful for linter, scope analysis that links assignment and SSS, which allow you to link different nodes in the tree. So you know they are referring to the same variables. We also provide qualified name information and also integrate with higher type checker, which provides us the inferred type given a node. And those are building blocks that make you build commas or linter. More powerful comma and linter is the.
Some of the stuff that Jimmy was mentioned is provided by this metadata framework that we have in libCST, which basically lets you say, oh, I have this CST node because while visiting the whole document, I happen to, pick this because it's an interesting import, for example. And then this metadata API allows you to query interesting things about that particular CST node. Like, for example, as Jimmy mentioned, like position, where is it in the original document? Or with the Pyre integration, you can ask for what type of this symbol that's being imported, for example. And there are like, 6 or 7 different metadata providers, and you can also implement your own. So like, with this framework, like it's an extremely powerful framework. You can do some like surprisingly complex analysis of the source code that you're transforming at the moment. For example, the most complex like analysis that I know of, it's implemented by the scope provider within libCST, and it allows you to figure out which symbol is exactly defined where it's being accessed, and it implements all sorts of like weirdness that you as a Python user might not know about, like, for example, name shadowing rules and whatnot, and especially with the new like walrus operator that became a bit tricky to implement. So reasonably complex analysis that kind of approaches what the type checker can do. It will never reach what the type checker can actually do, but like you can, use libCST not just for code mods, but for like reasonably complex analysis like this as well, using this amazing metadata framework.
Digging into libCST itself, can you talk through how it's implemented and some of the internal architecture and design choices that you made when you were structuring it?
So we didn't build everything from scratch. We try to reuse available parsers, Pigeon tool. What we use is a for parser library. So what provides by this library is it allows us to define the grammar and the conversion functions. So what we need to do is to take the grammar defined by Python documentation, the grammar of Python, and we need to build a lot of different conversion functions to process the output written from the parser. So our main logic would be focused on how do we want to preserve all those parsed value, especially the formatting values, and how do we want to define our nodes in the concrete syntax tree. So we need to carefully design the values, how those formatting value would we want to preserve. We try to carefully review different cases of white space, comma, and parentheses, try to think about their use cases, and then decide which node should own them. Yeah, so this is early work of the implementation of libCST. So we would need to implement a lot of conversion function, and we add a lot of tests. And of course, we also make it strong typed. So it will be very easy and convenient to use. And in terms of some of the API, like the transformer and visitor pattern, you are able to register a callback function, like visit simple statement. By registering a function like this, you can have the function being called during the tree traversal. And in order to provide strong type annotation support, we automatically generate the type annotation for all those callback function hook. So we actually use LibCST to call mods in LibCST to generate a lot of those type hints, function definitions.
From like a bird's eye view, LibCST has roughly let's say 4 big components. One being kind of like the parser, like stuff that takes Python code and converts it to something that you as a LibCST user can use. So that the parser. The second one is basically just a bunch of classes that describe the CST itself. So like things like, here's how an if statement looks like, here's how while loop looks like, stuff like that. So those are all just like a bunch of classes somewhere in the API. And the parser outputs these objects, basically. So that's the second component. The third big component is what Jimmy mentioned, all this visitor and pattern matching and traversal APIs, which are generated from the second component. So these like class definitions and whatnot, they're generated using libcst, as Jimmy mentioned, which was a bit confusing for me originally, but now I kind of sort of maybe understand. Last big component is the whole like CLI framework on top of all of this. So essentially, libcst is intended to be used is like there is already a code mod for use case. You just have to invoke it. Like there's a CLI interface that you can parameterize. It can handle like big projects with like Python roots and multiple files, and all of these things are in this whole like fourth component.
In terms of the evolution of the project, I'm curious, what are some of the ways that the overall scope and design and goals of the system have changed or evolved since you first began working on it?
Yeah, I think in the beginning, we focused on building the concrete syntax tree, build a parser, and also build the basic visitor and transformer API. This API also exists in the Python AST library, and so we try to use the same pattern. And after we have those ready and start to use it in our linter use case, we found sometimes when you have a lot of callback function registered in your tree visitor implementation, it can be very messy and complex. So we decided to spend some effort to make the traversal and modification easier. So that's why we built the mature pattern. With mature, we can describe the shape of a subtree that is easier to the code reader and easier to maintain. In the beginning, we also try to build some basic static analysis, like the position metadata for our linter. The linter needs to report the line number of a linter warning to the IDE, so the IDE can show the error in line. And later, when we start to build a lot of linter, we run into some ask that the author of those linters, they want to have more powerful static analysis. So we starting to build more static analysis, including scope analysis and the qualified name provider. So basically, I would say we evolved the library based on our clients. So we, as an infrastructure team, we try to provide this as a tool. All the other engineers in Meta and some engineers, they have different use case, and we will base on the ask to prioritize our work.
One of those engineers was me. I started using libcst in a surprising way. I didn't use it for code mods. I used it for code analysis. And so, I mean, technically, when I started working on the project, this was already a goal for me. So it wasn't really a change. But in terms of the project, I was focusing a lot on the analysis capabilities of libcst. So that's how I got onboarded, actually. And then over the course of the past 2 years, what has become apparent is that libcst is really, really powerful API that is very pleasant to use. And lots of people who want to manipulate code want to use it, but sometimes they can't because, it's not the fastest piece of code around town, because that was never a design goal. Like being fast was always secondary to being expressive and powerful. And so libCST was, and it is still used the majority of the time in offline mode. Like, I have these 100,000 files, apply this code mod to them, please. And then it's okay if it takes, I don't know, a minute more. But sometimes, especially more recently, people want to use libCST in more interactive sessions like IDEs. Like, I want to remove all my unused imports, but I don't want it to take a minute, please. And so, like, these people cannot use libCST or more complex code mods today because it's just too slow. Like, just to paint you a picture, like ID operations, they need to complete within 300 milliseconds. Code mods can take multiple seconds easily. That's just a no-no. So that's something I see nowadays that is changing, like this shift in terms of goals. Performance is slowly shifting upwards in the priority list. That's what I'm trying to say, I guess.
And I'm curious if you've had any attempts at just running it through Python to see if that improves some of the operation speed at all, or if it's just because of the nature of the changes that it's operating and just like the I/O that it has to do with the files that causes it to slow it down a lot.
Yeah, honestly, I haven't, but it's on my to-do list. Not Python, but more MyPyC, actually. Because the code base is already well typed. I think running MyPyC should be fairly straightforward on it, but although I've said the same thing about Black, and it was a 1.5-year project. But yeah, we'll see. That's one of the opportunities we're exploring. The other thing I've personally explored, actually, is because we needed to add support for Python 3.10, and the parser that libCST used to be based on was Parso. Parso does not support 3.10 grammar because it's an entirely different type of grammar. Not sure if we need to go into the specifics here, but like basically Parso doesn't support all the features of Python 3.10. And for a code mod tool that's being applied to code that can potentially include 3.10 syntaxes, like features, we need it to support 3.10. I went ahead and rewrote the parser from scratch in Rust. And yeah, I know. Yes, in Rust. Part of the reasoning behind the choice for Rust was because it gives us in the future opportunity to optimize the parsing side of things, which admittedly is not, the slowest part of libCST. Generally, the slowest part of libCST is visitation and the transforming. So parsing is, I don't know, like about 300 milliseconds for a typical 2,000 line document. That's not terrible. But because performance is slowly shifting upwards in terms of the priority list, which was made to write this in Rust. So in the future, if this becomes the bottleneck, then we'll, have the leverage. That's how I rationalize it.
Or just because you wanted a new project to keep yourself busy with.
I mean, if I'm completely honest, this was a hobby project. Like, it's just like on my spare time. And then I realized, oh shit, actually, we need this for some business cases. And then I was the furthest along. So we just went ahead and did it my way. But honestly, I probably wouldn't rewrite it in Python, even if I had given the chance, because what I realized is that, so one of the high-level design goals for libCST is it being well-typed. And the biggest gaping hole in terms of the type safety within libCST is the parsing, because Parso is untyped. And also it's very, very hard to express the types of transformations that the parsing, function needs to express in Python's type system. It was just like not done. So it's completely dynamic. And then we assume that the types are correct on the output side of the parser. And that turns out, of course, to be incorrect in some cases. And there are several bugs in libCST today that are caused by, parser returning slightly different types. Like, they make sense, but they're not the ones that are being advertised. So then, I don't know, sometimes they don't have an extra comma attribute, even though you're not supposed to put commas there, but the type allows you to. And I consider that a bug. And then the reason I bring this up is because during the Rust rewrite of the parser, I bumped into this all the time because Rust type system does not allow you to mess around. So I had to figure out what is the correct type to return and implement it, file a bug. And then eventually when the old parser infrastructure will be turned off completely, then these bugs will be killed for good.
Rust is quickly becoming the companion language for Python and slowly replacing C for a lot of the native code that you're plugging into Python libraries. And
yeah, close to hardware code, yeah.
And so in terms of actually using libcst, I'm wondering if you can talk through some example workflows of saying I either have this code mod that I want to do, maybe some examples of the types of code mods that you would use it for, and then the process of actually maybe interactively exploring what are the changes that I need to make, and then being able to turn that into a module and make it part of your maybe standard CI suite to make sure that, we never want to have this specific code pattern. We always want to make sure that this function name is actually translated to this, or that there are no function signatures that have 3 parameters because it's actually supposed to have 4 now.
One of the challenges about answering this question is there's lots and lots of internal tooling at Meta that makes most of these answers easy internally, but there's no real good open source solution. And I fully admit that part of the weakness around libcst is all the open source tooling. This is great, but now I want to enforce these rules in my code base. There are no tools that I'm aware of that allow you to do this painlessly the way I'm used to doing it internally at the company. So that's something that we might explore in the future. But at a high level, assuming you want to run a code mod that already exists and you don't have to write it yourself, you discovered it by, browsing documentation or a colleague tipped you off or something. What you do is you just take your Python source code, you just run the libcst CLI, choosing your code mod, and then maybe passing on some parameters, seeing your files change, making sure that changes make sense, and then automating it, writing a script that runs as part of your CI, and then either flags pull requests or just automatically checks in code. We do both approaches sometimes internally. Some of our code mods are actually run on the entire code base every day. Formatting is one of these, but also removing unused imports and stuff like that. They're just being run, producing pull requests, being accepted automatically, and just good to go. Does that answer the question?
Yeah. And then, for example, if I have a code mod where I want to restructure a set of modules, so I've got a function definition that I actually want to move into a different lib module, and then I want to make sure that all of the imports across the project are updated to use that new module location, what would be the process for actually writing a code mod to do that?
For this particular one, there exists a code mod, so you don't have to write it yourself. You just call libcst.tool, something, rename, and then pass in old name and new name, pass in all your files, and make sure that the Python root is set correctly so that the import, the fully qualified names are set. But if you wanted to write a new code mod from scratch, my process for this is starting always with the visitation API. And so figuring out what are the patterns I need to match on and what do I need to change them to. Myself, I look at the matcher API first because they're extremely expressive. So you just put some decorators on your visitation function that will make sure your visitation function will only get called when the node matches this particular pattern. For example, it's within an else branch of an if with a particular condition. So you can put some crazy things in there in a decorator, and then your function will only get called in those conditions. And then you basically say, okay, now I'm in the code that I care about. I transform, let's say for your example, renaming imports and symbols, you would be interested in visiting all the name CST nodes. And then in your visitation function, you say, oh, I'm in a name node. Let's check if the name of this node is equal to the old name. If it does, then emit a different name node with the new name. And then the catch here is you want to do this in an intelligent way. It's not just Control C, Control V, but more you want to figure out, if this name actually refers to the same thing, even though the name is different, but it's imported as an alias, for example, then suddenly you need to be aware of not just checking the value inside the CST node, but using the metadata APIs we talked about earlier. There's a metadata provider called qualified name provider or fully qualified name provider. And you just say, fully qualified name provider, please give me the fully qualified name for this name node. And then you compare that to your old name string.
As far as being able to do refactorings, like that of sort of restructuring modules or ensuring that function signatures are updated everywhere. I'm wondering if you can do some compare and contrast to LibCST offers as a sort of foundational library to build these type of structures versus what something like Rope might have out of the box.
I think LibCST try to provide both low-level APIs for providing the concrete syntax tree and traversing the syntax tree easily. So if your use case collects some knowledge by analyzing the syntax tree, then you will probably want to use LibCST. But if your use case is a very concrete about you just want to rename some function or move some functions around for common refactoring needs, I think Rope already provides a lot of feature to support. So I would say if you just want to do some common and simple refactoring, you can start with Rope. But if your use case require understanding the syntax tree by doing some custom analysis, or the command you want to do is very customized, then I think LibCST can help more those cases.
If Rope supports your use case, it's probably fine. Although that's the same for LibCST. If there is a code mod for your use case for LibCST, that's probably also fine. The question is, when none of these, like there's no existing code mod for your use case, then good luck with Rope. I would definitely use LibCST.
Yeah, absolutely. And beyond just the code modding use case that we've been discussing, you also mentioned that your original reason for getting involved in LibCST, Zsolt, was to add in some of these linting capabilities. And so I'm wondering if you can talk through some of the other types of workflows that you might build on top of LibCST, and for linting in particular, why you might use LibCST in place of or in addition to something like Flake or PyLint.
Flake is a pretty common linter open source tool, and a lot of people use it. But one feature we have found it's missing is autofix. So if you compare this linter with ESLint, you can see some of the linter from ESLint can provide autofix. And we think autofix is useful and important, especially in a large organization like Meta. You have hundreds or thousands of engineers. If your linter just surface an error to them and they need to manually fix them, then we think having engineers to manually work on those trivial fix is a waste of their time. We want them to be able to focus more on developing products. So we want to provide autofix for them. So what we have been doing after build LibCST is we built a linter framework. It's also open sourced. It's called Fixit. And in Fixit, you can easily define and implement a linter rule that provides autofix. We actually try to provide autofix for some lint rules provided in Flake. So yeah, for example, if you look at Fixit, you can see there are more than 20 we open sourced. And internally, there's a lot more custom rules we provide. I think overall, there's more than 100 rules. And a lot of those rules can provide autofix. For example, there's a rule called no string annotation. So in annotation, you may use a string quoted type, and we think that is less readable. The IDE may just highlight it as a string, but if you don't use the quotes, you make it real type, IDE can provide better syntax highlighting, which is more readable. So define something as a best practice and get a consensus from everyone. You can start building a lint rules using Fixit. And the autofix we provide from this rule is to automatically remove the quotes from the string type annotation. So what the end user see, their IDE is a button, so called Fixit. So we built a VS Code plugin that automatically call our Fixit linter, and whenever there's an autofix provided, it will show a button. So the engineer can just one click to fix it. And we think this can save their time, get them focus more on business development.
Yeah, so essentially, like TLDR is Flake started as, hey, there are some bad patterns, let's find them, which is a valid approach to linting. But it's completely different to the fix-it or libCST approach, where it was a code mod first, like we should fix it first, and then we can also like flag them to users in their IDE. So it was like kind of the other way around. Because Flake8, I believe Flake8 does have some kind of auto fixes. They're just kind of hard to implement.
One of the interesting challenges in these kind of situations is that Flake8 is a valuable tool that a lot of people have invested time into adding different plugins and additional linting rules to be able to surface those errors. LibCST is a project that's able to identify those errors and automatically fix them, but doesn't have the ecosystem around it yet. And I'm wondering if there's any opportunity for being able to either automatically use some of the rules that are defined for Flake8 and translate them into a syntax that libCST can understand so that you can use fixit to automatically resolve them, and just what that process will look like for being able to build up the capabilities around libCST and fixit to sort of get up to a level of what the Flake8 ecosystem has already built up.
Yeah, you know what? Great minds think alike. I think that's exactly what Jimmy was alluding to when he said sometimes fixit takes Flake8 rules and just like provides auto fixes for them. I think that's exactly what's happening there. But Jimmy, correct me if I'm wrong.
Yeah, so because Flake8 provides very different API for implementing linter rules and traversing the syntax tree, so what we end up doing in Fixit is we are calling into Flake8 to reuse some of the existing rules. But in order to provide autofix, we still need to redo the implementation using libCST for finding the problematic code pattern. And on top of that, we add the autofix logic. But I think what you described would be ideal. That is, we can automatically convert Flake8 pattern finder as libCST finder, but that doesn't exist yet.
Pull requests are accepted, though.
I was just going to say, it sounds like a community contribution waiting to happen.
Exactly.
And so digging a bit more into the Fixit project, which is actually how I initially came across libCST, I'm wondering if you can talk through just some of the structure of that and maybe some of the ways that you're using both libCST and Fixit in your own work.
So before we have Fixit, we try to use AST to develop a linter, and we build it as a Flake8 plugin. We start having a AST visitor to traverse the code and find patterns. And over time, the visitor just become very complex because a lot of different rules try to implement different logic on the same visitor, and that makes it hard to maintain. So when we get a chance to implement a new framework to solve the linter problem, other than autofix, we also want to make linter is easy to implement and maintain. So each linter rule can implement its own independent visitor. But with this, if you have a lot of linter rules, let's say 1,000 linter rules, if you need to traverse text tree 1,000 times, then it will become slower over time. So in order to be able to traverse fast and also keep the code separate for each linter, we designed a batchable visitor, which can allow us to combine all the different callback function registered from different linters. We batch them together and we apply them in just one single syntax tree traversal. Given a source code, we can just parse it as syntax tree and traverse it once. And while running all those different callback functions from different rules, we allow them to have separate context for their logic. So this is one design we had for efficiency of the linter run. And we also try to make it very easy to test. So in a linter, you can just define some test case, just like providing code examples. You would use the automatic document generation that take those code examples and generate them as the wiki page you can see on Reader Dots. And those code examples are also used in automatic unit testing. So we wrote a framework. So when you implement a rule, you can provide some valid code examples, and some embedded code examples. For embedded code example, you will want to also mention what are the expected lint errors you want to show to the user. And those will be used as example of the linter to the end user. It will also be automatically run as unit tests. And we found this approach make it very easy to develop the linters. So with those in place, we were able to develop a lot of linters rules, run it efficiently.
And in terms of the applications of libcst, now that it's been available for a while and open to the community, I'm wondering what are some of the most interesting or innovative or unexpected ways that you've seen it used?
I have several. This is both to Jimmy. Did you know that basically like most of the Google Cloud Python libraries ship with libcst code mods to convert between major versions of their API? I think that was pretty cool. I discovered this a couple of weeks ago when I was debugging why the hell is libcst downloaded so often. The other two that was kind of like surprising to me is some crazy person decided to write a Python indexer that emits basically information that's required to do kind of a GitHub-like jump to definition and find references information using libcst. This crazy person also works at Meta and is now powering basically all of our IDE services in the browser and in VS Code. And then the third one, it's less crazy, but it was surprising to me that people wanted to use libcst in an IDE setting where they wanted to refactor, just code, remove unused imports and whatnot.
Yeah, I don't have much unexpected, surprising use case. For the interesting use case, I think libcst has been used to solve large-scale tech debt problems, like clean up unused code, and also convert your code base to adopt async IO. You will need to convert the function from non-async to async function, and for each async function call, you need to add a wait. Those seems easy, but in a large code base, it's a lot of work. I have seen some people use that and shared a blog post talking about how they use libcst for their async adoption. It's also used for type annotation adoption. So in a large code base misses a lot of type annotation. We want to automatically add some type annotations rather than manually do all the work. And Monkey Type is an open source tool, open source by Instagram, and it actually uses libcst for inserting the missing types that collected by running the program. I have seen a lot of people use Monkey Type as well.
Can I also mention a crazy use case that I wish existed, but it doesn't? I wish, this has been my pet peeve ever since I knew about libcst, I wish Black would be implemented in terms of libcst. That's my goal in life now, to make that happen. I mean, even the original maintainers of libcst, including Jimmy, was like, why would you do this? Like lib223 is way better suited to Black because you kind of manipulate white space. That's the entire point of the project. And there are some downsides to the libcst approach because white space might get attached to completely different parts of the syntax tree, even though they're like syntactically right next to each other, especially during like boundaries between indentation blocks and whatnot. But I still think Black would be better off if it were implemented in terms of libcst, or libcst would be better off if it were made an API that made Black's implementation easier.
In your own experience of building and working on libcst and building other projects on top of it, what are some of the most interesting or unexpected or challenging lessons that you've each learned?
Code quality is important and hard. Way harder than I thought.
And just rewrite everything in Rust.
No. Don't. In fact, no. Just don't rewrite stuff in Rust without a good reason. No.
I think working on libcst and make it open source is a new experience to me because I think it's very different than a internal project, because internal projects we can try to develop fast and we don't need to do a lot of work on documentation. But when we decided to make it open source, we think documentation is important. So we try to use auto-generated documents and try to add a lot of documentation to major class to their doctrine. And also we try to increase the test coverage to make sure we have good practice. The entire project, we also bring in the popular linter tools and set up the CIs on GitHub to validate our changes, use pull request, which internally we are using a very different set of tools. And we also try to design a logo for our project. So internally, we have some designers. So by brainstorming with them, we come up with the final logo, which what we try to represent is a tree with a lot of leaves, which are the syntax tree with a lot of nodes. Yeah, I think overall it's a interesting and good learning experience to me.
I mean, maybe we should include the part about, hey, documentation at Meta was not important, but open sourcing made us realize it's actually important. But I do definitely agree with Jimmy's experience. Like, I've been a maintainer for quite a while, so I know the open source experience, but writing something that's mainly driven from internal use cases, but also making sure that it's actually not just a usable, but a pleasant user experience for open source, it's a major challenge. And it's a lot of effort. It's very hard to justify internally. Like, why are you working on this? Well, because of open source users, but there are these 10 other more important things that you could be working on. And so instead, what ends up happening is you still deeply care about the project. So you do the work over the weekends and whenever you have time, and you're trying to squeeze it in. And then like the end result is kind of subpar. So I don't have a good solution to this, but it's definitely a lesson I learned is that, I mean, I knew that open sourcing something from an internal code base was a lot of work, but just like way more than I expected. It's a lot of continuous work that doesn't get easily recognized, even from the open source community. I don't think I've seen anyone say, hey, good job, LibCST maintainers. I don't expect that's not how open source works. It just like makes it even harder to justify all the work that's required to make this pleasant.
Well, consider this interview your good job.
Thanks.
And so for people who are looking for a way to be able to parse and maybe code mod their projects, or they're looking for a way to be able to do round trip parsing and regeneration of their code, what are cases where libcst is the wrong choice and maybe they're better suited with a different concrete syntax tree, or maybe they just need an abstract syntax tree, or just something like rope and they actually don't need a parser and syntax tree analyzer at all?
Wrong choice? What do you mean? I don't understand the question. libcsst is always the right choice. No, in all seriousness, if you're looking to write a code mod, libcsst is a really good choice. There's very, very few cases where I wouldn't recommend libcsst if you're writing a code mod. Having said that, like if you just want to make sure that the code is syntactically valid and it's never going to be read or used by a human, then the complexity of a concrete syntax tree is usually not worth your time. You're usually better off either regular expressioning it, or if you're doing something more complex, then using an AST. And, like if there's an off-the-shelf product that does what you need, to just use it. You don't need to re-implement your logic within libcsst just because it's cool, although that's a fun weekend project and you can learn a lot. In general, I think like libcsst hits the mark on a lot of points when you're writing code mod. So generally, I would err on the side of using it than not.
Yeah, and I think I do aware of some cases that cannot be supported by libcst. Imagine in your IDE, you want to build some code automation based on the draft the user have. And that means that the code is not completed yet. It's not a valid Python code. libcst cannot parse those code. So if you want to build some very smart automation that can autocomplete the Python code in IDE, you will need to find a different solution.
Yeah, today that's entirely true, and that might change in the future if I get my way.
Speaking of the future, what are some of the things you have planned for the near to medium term of the libcst project, and maybe also for Fixit if you want to dig into that?
I can talk about libcst, not so much Fixit, because libcst is my current focus. Obviously, we want to keep up with new language features. Python is evolving quite fast. Like once a year, major release usually introduces a new language feature. we do want to be on top of that. So LibCST already supports 3.11, I believe. So that's a given. The second big thing is I want to make sure that the traversal of nodes in LibCST is fast enough so it can support more interactive use cases, with the caveat that Jimmy just mentioned. So like, even if it's fast, we will still only be able to transform, analyze, modify valid Python code. So in fact, that's the next priority item is now that the rewrite of libcst's parser is slowly but surely wrapping up, now we will have a chance to change the parser so it can accept invalid Python code, and then have some boundaries where it says, okay, yeah, this expression is invalid, but I can still parse the rest of the document and you can still operate on them. So that's something that we might be looking at. No promises, we might be looking at in the future.
Are there any other aspects of the libcst project or some of the ways that it's being used both in your own work and in the community and just sort of code modding and concrete syntax trees in general that we didn't discuss yet that you'd like to cover before we close out the show?
I think as Zsolt mentioned, we still need a lot more tools that build around libcst in the open source world in order to make it more easy to use. For the other popular tools like Black or Flaky, I have seen a lot of people build a lot of tools to make them very easy to use. Like they have GitHub Actions, so you can easily enable Black or MyPy on your GitHub project, but libcst is missing those. And at my work in Carta, I actually also try to use libcst, and we are using GitHub for our code development. So I have been trying to developing things around GitHub and libcst and fix it too. So I have trying to build some code mod service that automatically create GitHub pull requests, and hopefully in the future, if some of my work can make the open source ecosystem more useful.
You should definitely take a look at one of the picks I have picked for later. It's called Auto Transform. And if you remember Code Mod Service from internally, that's the open source version. And the guy who wrote Code Mod Service writes that. Highly recommend. It is growing a libcst integration as we speak.
All right. Well, speaking of the picks, for anybody who wants to get in touch with either of you and follow along with the work that you're doing, I'll have you each add your preferred contact information to the show notes. And so with that, now I will move us into the picks. So to get us started, I'm going to pick the Osprey Manta backpack. I got one recently, and it's definitely a major upgrade for some of the other packs that I've used. I particularly like the sort of support structure that it has against the back that keeps the bag off of your back so you get nice airflow so you don't get all sweaty when you're out and about hiking or biking. So recommend that if you're looking for a pack to wear when you're out and being active. And so with that, I'll pass it to you, Zsolt. Do you have any picks this week?
Yeah, but they are unfortunately boring and related to code. So Auto Transform is one of mine. Just a quick shout out to Nathan, who's working on it. Just Google Auto Transform GitHub and you'll find it. It's a service that automates your code mods for you. So it's like a way to, once you have a code mod that transforms your little source file and to the desired state, this service will let you apply that across all your hundreds and thousands of files in an automated way and not lose your sanity. The other pick is go to glean.software in your browser. It's a cool little database project that allows you to store facts about any kind of source code. And I'll just leave it at that. You can discover it for yourself.
All right. How about you, Jimmy? Do you have any picks this week?
I don't have a specific pick, but I would like to share something that is related to libcst and CodeMod. So I think after being work on a lot of different projects and in different companies, I have seen that tech debt is a problem that we always face. And it's hard to make the decision whether we should fix those tech debt right now, or because there's always more important or urgent product development requirements. I think that's one of the motivation we want to build the automation to fix them. But not all the tech that can be auto-fixed. There's still a lot of more complex tech that it requires engineer to develop it. So we want to make sure when engineer proactively work on tech debt, their contribution will be recognized. So what I have been trying to do in my previous few projects is to analyze the commits to the code base to figure out what kind of contribution the developer make to solve some of the tech debt. For example, maybe they help missing types or they clean up some unused code. With a automatic analysis, we can summarize their contribution, and we try to use those summarized contribution to provide the numbers about their contribution as a reference to recognize their contribution. That's a philosophy or a strategy I have for large-scale tech debt problem.
All right. Well, thank you both very much for taking the time today to join me and share the work that you've been doing on LibCST. It's definitely a very interesting project and one that I'm glad to see as part of the ecosystem. So I appreciate all of the time and energy that the both of you and the rest of the contributors to the project have put into that. And I hope you enjoy the rest of your day.
Thank you for all the work you put into the Python community at large. I've been an on and off listener to the podcast, by the way. Good job in general.
Thank you.
Yeah, thank you for inviting us. I'm so happy to share our experience with more people.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.